over the safety for the lab. And so I was just going to, is there anybody who has not picked up their lab kits yet?
I haven't gotten mine yet. I just made an appointment today.
Oh, perfect.
Yeah, I get mine this afternoon too.
Excellent. Yeah, because that was one of the things I was going to go over. If everybody had already gotten them, I was just going to skip it. But I guess that's why we didn't really get to start doing the labs this week, because it takes a while to get everybody set up, get their lab kits together, everything like that. So I was just going to basically go over how to do that in case you were slightly unfamiliar. Then go over some of the safety considerations, because it is a little odd that we'll be doing labs at home by ourselves, and those are basically two things that you're never supposed to do when doing experiments. You're usually supposed to be in a lab where there's all the safety equipment everywhere, and there's someone to supervise you, and all that sort of thing. So we generally don't do it this way, which is why I think it's a good idea to sort of talk specifically about how to deal with these, home experiment situations. And then Dr. Schubert has put together an activity for us to do after that. So I imagine we'll probably be here for about maybe an hour today. And then we'll call it a day. And then next week we actually get to play with our experimental setups. So does anybody have any questions before we get started on either the course or the lab part of it?
Get the sapling code, because I still haven't gotten that.
Oh, okay. So did you try to get it from the bookstore and they told you that it was sold out or something? That's been happening a lot.
It was back ordered, I think.
Right. You can get it directly from the company rather than going through the bookstore if you want, and that way you get it immediately.
Okay.
I actually got my email today, so I'm picking up before class Thursday. So they might be giving them out soon.
Oh, okay. So when did you go and order it from the bookstore?
So I ordered it like the first day we had this class, basically. So it took a while, but I got the email. But I already picked up my lab kit, and I was like, "Oh, what's the deal?" And like, "Oh, it just ships separately, and it's a physical copy they hand you."
Yeah, it's odd, but I think. Oh, damn phone. I think we can also get it directly from the company, and they'll just send you.
Yeah, but so you can pick either pick up or ship, but I picked email, and if you pick email, then they send it to the school.
Really?
Yeah.
Huh. Okay. Well, I'll find out, because I think there's already a sapling assignment, right?
I think so. Yeah, because I called the bookstore and I was like, "Oh, I told them to email it," and they're like, "Oh, we have it."
Yeah, it's so bizarre. I mean, it's just a series of numbers and letters.
Yeah.
Why it's back ordered, I have no idea. That's not how
send it right to you.
The information superhighway is supposed to work, right? It's so bizarre. Oh, so someone, you were able to get it on Amazon?
Yeah, I got
Amarani, you got it on Amazon? That's bizarre.
Yeah, I did.
I didn't even know that was available.
I didn't even know that it was a code. I thought it was a book, and I get all my books from Amazon. So when I ordered it, the code actually worked, so I was able to get into sapling with it.
Cool. So how much was that? Was it the same price as at the bookstore?
I think I paid around $46, so I think it is roughly around the same amount.
Yeah, I think so.
So yesterday I picked up the kit from the STEM Center at Skyline College, and today I picked up from the bookstore all the things, and they give me a package, and then I opened it just to confirm, and they were missing the sapling inside. So I went back, and they told me that they got the sapling last night. So when you purchase that on the bookstore online, it says print.
Right.
But actually what is print is the code printed in a paper.
Right. It's kind of ridiculous.
Yeah, and it's $50 for it. And then if you get it online, it's $42.
Well, there you go. Yeah.
Yeah, it's cheaper directly from sapling.
But you said they don't send the email directly to you, but to some, like to the department or something? I mean, or to the bookstore, it sounds like.
Yeah, I guess they have like physical cards that they hand you, which is weird.
Okay. Well, it sounds like they should all be available by the end of the week. So, Davey, you said that they got a shipment last night.
Yeah,
So,
that's what they say. That's what is included into the box with the rest of the things.
mhm.
I don't know. So if you have to pick up something, just check your box before you leave, because maybe you're missing the sapling or something else before you
Okay.
leave the.
Yeah, it's always, yeah, I mean, it's always a good idea to try and limit the number of visits on campus as much as possible. That's for sure. So any other questions before we get started? Nope. Okay.
I have a question.
Oh,
Sorry
sure.
for doing that. I have access to the sapling, but it all says Schubert, even though I'm registered for your class. Like I have.
Oh, right.
RS.
Yeah,
Is
yeah,
that
yeah.
normal?
So, but you're in, which section are you in? What the CRN number?
Like 43697.
Yeah, that's
Yeah.
that's us.
Yeah, I also have that issue.
Me too.
Well, okay, then it sounds like, with the sapling, that is strictly the whole class, not just the lab section. That's the whole class. So for sapling in particular, yeah, that'll be under Schubert, since she's the main instructor for the class. I'm the lab instructor. So anything lab related should have my name on it. But if it's not lab related, it'll be with her name on it. So yeah, it is a little confusing for people because because of the way the course is set up, where there's like a main instructor and then there's two lab instructors, and so I think that's where some of the issues from. So don't worry about that.
Thank you.
Yeah, just lab related things, like your pre-labs and your lab reports will all be coming to me, and then it's like everything else, and everything else will be going to Dr. Schubert. Okay. All right.
Well, for Thursday sessions, do we also come to you or do we go to her?
Nope.
Okay.
Yeah, labs and recitations. Yeah, we'll be us together.
Okay.
Yeah.
Oh, and I have another question. The
Okay.
recitation you put up, I still only had Schubert's. I never got the yours that showed up on Canvas. Remember, we were supposed to turn in the recitation or whatever.
We don't turn in the recitations. So what was there an assignment?
I think you put up like when we had to do the group here. Let me pull it up real quick. It was the recitation talking about, oh shoot, where is it?
Is that the scientific method?
Scientific method, right?
Yes, yeah, that one.
Mm-hmm.
And you said that you put up an assignment link to like submit the rest of the paper on there, right?
I think so.
But I only have like whatever Schubert puts up. I don't have anything you put up.
That's strange. So that's Gage, right?
Yep.
All right, I'll check and see which group you're in.
Okay.
Because I think there's still some confusion.
All right. Well, thank you.
No problem. Was everyone else able to find that particular assignment?
I did, but I noticed that it kind of like pick and chooses who we're going to be receiving homework from. For example, I spoke to somebody that was in your class, but couldn't find it under assignments that he owes you homework. And for some reason, I understand that you want us to send a picture of our lab kit, but
Right.
Professor Schubert is also asking for that, which she's also giving out points.
Right.
But my fear is, for example, if you're asking homework from us and I don't see it, I don't want to miss or get a 0 for that homework if I don't see it.
Right. Yeah, I think it's as far as like the lab kits and the pickups, that sort of thing. Since everybody will be doing that, you can just if there's a submission you have to make, and there's only her name and not mine, go ahead and submit it to her. But if there's both of ours, then you would submit it to me. Okay. But I think she just wants to keep track of everybody's everybody in the entire class, both lab groups, whether or not they've picked up their lab kits, whether they have a full set. So I think she wanted to keep things centralized there. So you would send a picture and submit it to that particular place, which is lab kit pickup, Schubert. Since she's not actually teaching either one of the lab sections, she just wants to keep track of who has lab equipment, who doesn't, who needs to get additional lab equipment from the department, that sort of thing.
And is it a technical issue as to why sometimes we can't receive homework from your end?
I don't know. I need to, yeah, these sort of, little niggly details sort of tend to shake out after like the first couple of weeks. I think I may have posted in the wrong place. So I'll go back and check to make sure I'm posting it in the right place. Cause I've got like, four different canvas shells to put slot things in it. I just may have made a mistake. So I'll go back and double check.
Okay, thank you.
No, thank you for pointing these out. This is exactly what we need to know. Because yeah, it is confusing, especially because everyone builds their canvas shell somewhat differently. Some have it a lot more complex with a lot more tabs and everything else than others. And if you're going back and forth, it's sometimes difficult to find what you need. So I think we may be running into a little bit of that. So hopefully we'll clear a lot of that up as we go along. Let us get started. Okay. So it sounds like pretty much everyone has picked up their lab kit. Just for the few of you that haven't, I'll just briefly go over what it is we're going to be doing. So obviously you know how to schedule an appointment. It sounds like everyone has an appointment now. That is just the link to go do that if you haven't done it. And you're kind of running out of time because there's just basically till 6 today, and then Thursday until 4, and I think that's it. Although you may be able to schedule if there's for some reason something goes wrong and your car explodes or something, we may be able to work out additional times, but we'll have to see on that. So just bring some sort of photo ID. I'll show you where you actually come into the campus. It's a different route than the way I normally take, as I found out the hard way and had to go all the way around. Obviously have a mask. You don't even need to get out of your car. They will just, if you can pop the trunk remotely, they'll put it in your trunk, or they can just open the back door and toss it in there so you don't have to pick it up yourself. So for the pickup, when you go in, like what the mistake I made was that I went up to the normal place where I come in near building 7, in through College Drive, and that's all blocked up. So you can't do that. So what you need to do is go all the way around to Skyline Boulevard on the east side of the campus. And then you go in, and then there is, like on the first parking lot, there is a little, just a small building there with somebody in it who's basically checking IDs to see who's coming in, so they can keep track of who's on campus at any one time. You just show them your ID, say you're going to building 7, and they take your name down, where you're going, then make your way up to building 7, and don't even get out of the car. Just like basically stop. It's just outside the little roundabout where building 7 and building 8 are. So you just wait there, and someone will come out and put the kit in your car. So the only thing to really remember about that is like how to get in. I had to drive all the way around. So if you have any questions, Musa is someone you should get to know. He is the chemistry lab coordinator. He's, when we're all meeting in real life, if hopefully we'll get back to that in the fall. He arranges all of the labs, stocks the stock room, gets all the arranges everything, makes sure all the laboratory equipment is ready to use, all the reagents are laid out. So he takes care of all that. He's a really excellent guy. And so this is his email if you have any questions. And so, for some reason you can't pick up your kit, or something's missing or whatever, just drop him a note. He'll get right back to you and work out how to make sure you have a full working kit before we get started next week. You can also contact the bookstore directly, but I would email Musa first, because he knows specifically what's supposed to be in these kits, because he basically contacted the company and got them all shipped to him in the first place. So I just want to briefly show I just want to make sure you guys can hear it. Share computer sound. There we go. So this will just briefly go a little bit about basic lab safety, and then I want to talk specifically about at-home lab safety after that.
Some of the best moments of my life have happened in labs. Also, some of the worst. Like the time that I took a week to prepare a sample for NMR analysis, and then a classmate washed out the vials while I was sleeping for the first time in 3 days because he couldn't find anything else to use for his experiment. Interestingly, that resulted in my personal most significant laboratory injury. We all have one. I cut my hand while punching a paper towel dispenser in frustration. No one ever brought it up again. Today, we're going to talk about how to avoid injury in the lab and some good techniques for using laboratory equipment correctly. First 2 lessons already learned: never wash out a vial you aren't familiar with, and don't punch paper towel dispensers. Let's start with some very basic safety stuff. Your hair. If your hair is long, it shall always be up in the lab. If it is not, it will catch on fire. I've seen it happen. It can also knock stuff over and occlude your vision and droop into your flask. Same thing goes for anything that might hang off your body in the lab. Droopy clothing, especially sleeves, are a total disaster. Clothes should cover your body as much as possible. I like to go long sleeve even. Never, ever, 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 ever wear sandals in a lab. Long pants, closed-toed shoes, and socks. Clothing that covers your entire torso. Always. I'm sure you look hunky in your muscle shirt, and I have nothing against exposed midriffs in principle, but not in the lab. Of course, your eyes are your most vulnerable organ. Always wear eye protection, and no, just glasses do not count. And if you feel like your eyes are starting to tingle or hurt, or even if you don't know how something might have gotten in there, use the eye wash, because it never hurts to be careful, and we've all wondered what it feels like. I've actually never done this, so this will be a new experience for me. It does not feel particularly pleasant. But it's better than having your eyes burned out. Do not eat or drink in the lab. Despite our best efforts, stuff does sometimes get where we don't want it to be. And if it gets in your food or you accidentally pick up the wrong cup, that's just a really embarrassing story for your obituary. Also, I would generally suggest avoiding working alone in a lab, especially if you're working with any machinery or hazardous substances. But it will be up to you and your advisors to make that decision when the time comes. You may have seen this little symbol before here. It's the hazardous materials or hazmat diamond, and it's got some useful information in it. Each little box is rated 0 to 4, 0 being no big deal, and 4 being
Holy monkey, be careful.
blue is for health, the red is for flammability, and yellow is for chemical reactivity. A 4 in health means certain kinds of exposure will kill you. A 4 in fire is both very flammable and gaseous, so impossible to control outside of a closed container. And a 4 in reactivity means that it is capable of exploding at room temperature. The little area underneath is for any extra information, like if it's radioactive or reacts violently with water or something. If you ever need to know more about a chemical and what it might do to you or to the world, there's the good old MSDS, the Material Safety Data Sheet. Every chemical has one, and it'll tell you all the terrible things that it might do to you. If you ever need to find one really fast, you don't need to go to the cabinet anymore. You can just Google MSDS HCl or whatever chemical you think is in the process of killing your friend. There will be information on how best to treat the person who got exposed. Of course, you should have always read the MSDS before you even touch a chemical. Also, you should probably assume that every liquid in a lab that is not water is flammable. This baby here is a fume hood. It sucks all the air in there out so you don't have to breathe whatever's going on in there. It's also why it's impossible to keep chemistry labs at the proper temperature, because the AC units and heating units are constantly pumping in controlled air, and these are constantly sucking it out. So if you're doing some chemistry that might contain some noxious fumes, that goes on in here. And if you want it to work properly, first you got to turn it on. That's the vent. That's the blower. Now it is sucking air. Second thing you want to do is make sure the sash is at the right level. This has a little thing that tells you where the sash is supposed to go. If you go above that, on this model, it'll buzz at you. If the sash is higher than that, it's not going to properly vent all the stuff to the outside, and some of it might get into your face, and that would be bad. As a side note here, if something happens to you in the lab, and if you don't know whether it was serious or minor, you're not sure, just tell your instructor. I once inhaled a bit of nitric oxide, which, though initially extremely unpleasant, seems to subside after a while, but it can have longer-term effects. Headache, nausea, disorientation, dizziness, pulmonary edema, death. So I'm glad I fessed up so that I could get taken care of. Speaking of, if you want to know what something smells like, do not stick your face in it. Waft it toward your face. Also, never test something by tasting it, obviously, and never pipette by mouth. I hear people say that, and like, who would? But then I just found out that Heiko, the chemistry consultant for Crash Course, has twice gotten HCl in his mouth from pipetting by mouth, which I will never forgive you for. That is what these things are for. You put that on the end there, and then you go on, you draw the liquid up with this thing. That's what that's for. Also, these days, most pipetting is done by these guys, which are way cooler anyway. Pipetting is one way to move a substance from one container to another, and it's a pretty good one. But if you want to pour, you can pour. But let me just give you a tip. Commit. We tend to get all nervous when pouring stuff in the chemistry lab and go all slow with it, but that's terrible. You won't overcome the surface tension, and it'll dribble down the side of the container, so just commit at the beginning and at the end. Destroy that surface tension. Okay, back to safety. The most common lab injuries are cuts and punctures, and the most common source of those is cleaning up broken glass, which you should not do with your hands, but with a broom and a dustpan, and then deposit the results into a bin specifically for sharp stuff. But the worst thing, and it has happened so many times and it is so terrible, is forcing a glass rod or a thermometer or a piece of tubing through a stopper, and then it breaks, and then right into and through your hand, and you're in the hospital and you're in pain for the rest of your life probably. So when you're doing this, and it is sometimes necessary, you can use a bit of water or a lubricant or some kind of Vaseline to make it easier to go through, and then you hold it close and make sure your hand is not on the other side. So very close, and make it go through like that. Not like this, because that's, no. When you're done with an experiment, do not just dump the results into the sink unless this has been explicitly approved by the person in charge of chemical safety. For some chemicals, like common acids or bases, dilution is the solution to pollution. When they get diluted, all that's left is common ions like chloride ions from HCl or sodium ions from sodium hydroxide, in addition to some protons or hydroxide ions that are neutralized by buffer ions that are present in your sewage system anyway. Bottom line is, they can be flushed with lots of water. For other chemicals, flushing is not a good idea. That probably won't hurt you, but it might hurt the environment. Do put the products into an appropriate waste container, but not just any waste container. Different solvents and reagents have to be disposed of differently, and if you dump some stuff into the wrong container, it could totally end up reacting with the other things that have been dumped in there. Not good. Rule of thumb, always know the right way to dispose of something before you even start to use it. This is an apron. It protects you and your clothes just a bit extra in case you're working with something hazardous like concentrated acids. Aprons are nice because course, they're easy to get off if you spill something on them. Well, if you're wearing pants, you might hesitate a bit too long before you ditch them. Which reminds me, if you spill more than just a bit of anything super bad on your pants, modesty goes out the window. Just take them off. Also, while you're taking them off, you might want to run over to this guy here. His job is to dump a gigantic amount of water on you really fast. Now, usually, you don't get to see these things in action unless there's an actual emergency, but to thank you for sticking with us through this somewhat disjointed lecture on safety in the lab, I'm going to take this off. That's a lot of water! Thank you for watching this episode of Crash Course Chemistry. If you were listening, you learned what to wear in the lab, how to dispose of chemicals, how to avoid the most common accident in the laboratory, how to pour properly, what the hazmat diamond is, what an MSDS is, and how to use a fume hood. This episode was written by me. You to them. Sound designer is Michael Aranda, and our graphics team is Thought Cafe.
Okay. Yes, that is the truth about putting glass tubing into a stopper. I have a scar on my hand that I got 45 years ago because I was doing that exact thing in elementary school and put a piece of glass through my hand. So he's not kidding around when it comes to that. So that is basically involving working in a lab, which is something we're not really going to be doing this term. So, you know, you're not going to have an eye wash station. You're not going to have a safety shower. You're not going to have a fire blanket. You probably should have a fire extinguisher. That is a good thing to have. If there isn't one in your house, I would recommend getting one, because we will be using flame for some of our experiments. And so it's important to be able to put that out in case something goes wrong. So here's some of the safety considerations. Could everyone see my, oops. Why can't I get past this screen? Okay. God. Here we go. So now that we're going to be working at home, we're obviously violating some of those rules that we were just learning about, like never work alone. And what are the things that was mentioned in the videos, like the proper disposal of chemicals? So we've gone through and designed these experiments with reagents that you can put down the sink. So there's not going to be anything dangerous, like heavy metals, for instance. You never want to put those down the sink. Things like, you know, lead, the arsenic, you know, that sort of stuff. You don't want to put those down the sink. But acids and bases, and like, you know, sodium and that ions, potassium ions, that sort of thing, that's not dangerous in any way. So we can just flush it down with lots of water. It's not going to be a consideration. So here's some of you will be getting a pair of goggles in your kit. And I also have a checklist. I just posted on Canvas under the lab resources section, a checklist of everything that you should have in your lab kit. So you can go through it, and there's pictures of everything in there. So go through it and make sure you have everything. That's one of the assignments you're given after today's class. So if there's kids or animals in your house, I've got kids and animals in my house, You want to keep those away from them because it's, some of these things are not particularly dangerous, but you certainly wouldn't want people drinking like relatively concentrated acids or bases. That's a bad idea. So you'll have eye protection included. If you do have long hair, like was mentioned, just tie it up. Obviously not really a problem for me. And don't just take, I've got all these reagents, I'm just gonna, mix them together, because there are certain things like concentrated acid and a concentrated base. You put those two things together, they do release a lot of heat. And so they could get really hot, and you'd like drop it on the floor. You definitely don't want to do something like that. What's going to be tricky, I think, for a lot of us, including myself, is finding a safe place to do these things, right? I mean, not all of us are going to have their own home office. I mean, my wife's got one downstairs, but she's going to be using them during the day. So I'm going to need to find some place to actually do all this stuff. So it's got to be well ventilated. That's important. You're going to want to have it well lighted, and then have your fire extinguisher or whatever nearby. Also, no food or drink in the area, because a lot of times, even if there aren't a lot of fumes, you can get the chemicals on your hand and not even really notice it, and then transfer it to like a sandwich or a piece of fruit or whatever, and then all of a sudden you're eating them, and that's not a good idea. So no instruments, no materials near your mouth, and make sure you've washed your hands before and after. So yeah, you don't want people, especially when you're doing the experiment, you don't want people running through, knocking things over. If you can find a place that's flat, that's going to be really, really important. Someone mentioned in a different lab group last night that they were going to do it on their bed, and they said, well, that sounds like an okay idea, but it's not particularly flat. But they found like a big board they could put on top of it, and then that sounds fine, as long as, like, when you push it with your arm or press it, it's not going to tip over. So something flat and relatively large, because you're going to be putting different reagents in different places. You're going to want them all within grasping distance. You're not going to want to have to reach over and knock something while you're reaching for a reagent. This is super, super important. Never wear contact lenses. I found that students really don't like to do this. Like when you're by yourself, you're in your own room. Does it really matter that you have to like drag out your old, nerdy looking glasses to do the experiment? It shouldn't matter. But I know that, some students, and particularly the men for some reason, I don't know why, they don't want to wear glasses in the lab. They want to wear their contact lenses, but it's extremely important that you don't. And the reason is, if there are fumes, or if you do splash a chemical in your eye, what that contact lens will do is actually concentrate the chemical right on your retina. Well, not on your retina, but on your cornea. And so instead of being able to quickly rinse it out, those chemicals are going to be concentrated directly on the surface of your eye, and you won't be able to rinse them out. And so basically you're doubling down on it being a bad idea, because it concentrates the bad chemical, and it makes it more difficult to remove it. So it's a big, big no-no. Just wear your big dorky glasses like I do. Don't use large quantities of chemicals. You can see here from the picture that a lot of these things have been basically put into small bits of chemical or solution or whatever for you to use for a particular experiment. Just use that small amount. If it is comes in a larger container, just use as little as possible. Label everything. The worst thing you can have in a lab is to have a container with a liquid in it and not know what it is, because A, You don't know what it is. You don't know what you should be adding something to it. You don't know whether it's acidic, whether it's basic. You don't know whether it's safe to pour down the sink. You don't know what it is. And so always make sure that before you start any experiment, check and see, like in the video, it was a really good idea. Check the MSDS, or the Material Data Safety Sheet, to see what do I need to do? Is there something I need to know about this chemical? If I splash it on my hands, do I need to, be immediately rush to the hospital? Or if I just wash my hands, it's fine. So you can just Google all those things and make you a little more comfortable about using these. And so, yeah, one of the first experiments we'll do is learning how to make accurate versus precise measurements, because you want to make accurate observations and measurements, so you don't have to do the experiment over and over and over again, because then you're going to run out of reagents and then you won't be able to do the experiment. Obviously, don't smoke or eat around, particularly when you're doing flammable materials. Don't have the stove going if you're using even something like ethanol. There's going to be some vapor being given off, and you don't want to have a fire. In case you do spill something, and you're going to spill something. I spill things all the time. Have some. If you have some of the heavy-duty blue paper towels, like the shop towels, those are excellent for doing these. If you don't have the blue shop towels, that's fine. Pretty much any paper towel will do. Just use lots and lots of paper towels, sop it all up, and then you can basically just throw it in the garbage. Because like I said, we're not going to be giving you really hazardous materials that you're going to have to put in a plastic bag and then seal inside of another plastic bag and then call some hazmat unit to pick it up. Just make sure you do get it all up, and then rinse with water, and then clean that up. And then make sure you clean all the utensils you've used after you're finished. You're not going to have a fire extinguisher. You really should. I mean, it doesn't have to be something massive, just like one of the little ones that people typically keep under their sinks. Be a good idea to have, because like I mentioned, there will be experiments with fire in them. We're not going to be like, burning huge amounts or anything. Basically, like what you basically, like sterno that you put under a chafing tray or something like that. So it's not like a huge amount of fire, but it can be tipped over relatively easily, especially if one of my dogs comes running through. So we're gonna have to figure out what to do about that. And have a phone nearby in case. Always, you don't have to have the 911 dialed and then wait for the dial a 1, but just have it around in case something goes wrong. So we have posted the at-home safety manual. I don't know, does the safety manual actually come in the kit? I should know this because I picked mine up already. Does anyone know if it actually comes in the kit? If not, we've posted this on Canvas for you to check out. Most of it's for microbial cultures and stuff, but there is some for chemical safety here, just to go over, what are the chemicals in there, what you need to know about them. So here's sort of an example. You may recognize Rowan Atkinson as Mr. Bean here. So what he was going to do is like pour these chemicals together and they're going to explode. So what are some of the problems you see? Just looking at this picture, I can already see that there's a number of serious problems with it. So is he dressed appropriately to do the experiment? What do you think? What's wrong with what he's wearing?
He doesn't have goggles.
What's that?
He doesn't have goggles.
Yeah, number one, not wearing eye protection. Big problem. Anything else?
He has a tie on.
Ah, excellent. I was wondering if anyone's going to see that. Yeah, he's got this tie. And with the tie can flop out and get caught in something. Like I've been working in labs for 30 years, and I still, when I have long sleeves on, like I do. I'm constantly pulling them up. Always. It's just a nervous tick, basically. So you should have, like, you know, like the guy in the video was saying, you should have long sleeves, but not so long that they come down and, like, you know, you're reaching in and they fall. So even now, even though I haven't worked in a lab in a couple of years, I'm still constantly pulling them up so that they don't fall into anything. What else might be a problem here?
He's not wearing gloves.
He's not wearing gloves, right? I mean, you don't always have to wear gloves in a lab, but definitely if you're going to be holding two things like that and pouring them into each other, that's probably not a good idea to have bare hands. Should he be pouring them into each other while holding them up like that? How should he be pouring them?
Away from his face.
Number one, away from his face. That's an excellent suggestion. What else?
Depending on what it is. Don't you have to pour certain things under a hood?
Excellent. Yeah, you may have to pour things under a hood because you don't know. Maybe it releases a gas when you mix these two things together. That could be extremely dangerous. But even simpler than that, you should never be holding one thing in your hand and then pouring another thing into it. One of them should be on a flat surface. So it should be like on the lab desk or a bench or something. And remember, when you pour something, how should you do it?
Quickly or confidently?
Relatively, yeah, confidently. That's the best way to put it. Because like you've seen, if you have like a glass of water and you just sort of just tip it a little bit, what does it do? It just dribbles down the side of the glass. If you pour it with more of an angle, it actually comes out of the glass. So you definitely want to do that. What's one other thing that, just looking at it, that seems to be a bad idea?
They're not labeled.
Oh man, you guys are all over this. Yeah, neither one of those things is labeled. Excellent point. Yeah, so it looks like he's got like a clear liquid and a dark liquid, but we don't know what they are. So obviously he doesn't know what they are either. But the thing I was thinking about is that, yeah, he has his big nose, and you know, I have a relatively big nose, so I'm sensitive to these things. Yeah, he's got it right under his nose. As someone mentioned, he's pouring them together right by his face. So how should you, if you have two things, two solutions, and you know one of them has a slight odor and the other one doesn't, how should you check to see which is which?
You wave it towards your nose, like, yeah.
Right, exactly. Like if I had a beaker with alcohol in it and a beaker with water in it, well, I know the water's not going to really smell like anything, and the alcohol, well, it's going to smell like alcohol, but I'm not going to just stick my nose right in there. I'm just going to sort of waft it toward, and you'll be able to, oh, okay, this one's the alcohol, that one's the water. Right, excellent. So these are the assignments that'll be coming up. So you have the laboratory safety quiz that will be due, I think, by the end of today. It's due, and it'll be available till tomorrow at midnight. And then check the list. I'm going to just show you the list of things that should be in the kit and check those. So there's one for me, and there's one for Dr. Schubert. If you have any missing things, just put them in there, and we'll try and get them to you as quickly as possible. Okay, so do the safety quiz, check the missing items, and also submit whether you've picked everything up yet. Hopefully everybody will have picked up their materials by the end of this week, because next Tuesday we're going to start doing an experiment. So any questions about that?
For the practice assignment, if we don't have sapling by the time it's due, will that like affect our grade?
No, it's a practice assignment. Notice it doesn't have any points next to it.
Yeah.
So yeah, basically the practice assignment was just to get you familiar with sapling in the first place. So yeah, obviously if you don't have the code yet, for some silly reason, you won't be able to do it. But it's not like it's not going to affect. It'll only be like going forward. If you haven't got one by like the end of next week, that might be an issue. But it sounds like everyone should be able to get one by the end of next week. Okay.
On Canvas,
Oh.
and I don't see your assignment published for the missing items right now. I see
Okay,
Dr.
I'll check.
Schubert.
I'll check and see if they may not have been published yet. So which Canvas page are you looking at?
I'm under the assignments tab, the upcoming assignments.
Mm-hmm.
And for the most part, it all looks the same. It's just when it comes down to the missing assignments, I only have Dr. Schubert's.
Okay, then submit it there. Yeah, if you only see her name, just submit it there. If you see both our names, submit to me. It should. Okay. That particular part of the assignment it's not particularly important. We just want to make sure that they're not really even going to be graded. We just want to make sure that you have everything and what reagents are missing. But I'll double check on that stuff, because yeah, I've noticed that some things, like I assume at the green check mark, meaning it's been published, but some haven't. So let me go to. Oh, I was going to show you the list. Where is my list? Oh, there we go. Strange. Okay. Oh, here we go. So here's can everyone see this? The PDF that's open right now?
Yes.
Okay, cool. That's the problem when you've got like 18 windows open. It's kind of difficult to see which one you've got here. So this should be everything that's in the checklist. So this is the Principles of Chemistry set. And so these are all the things that you should see in there. So how can I write on this? Okay. So 2 graduated cylinders, beaker, all the test tubes and everything else will be plastic, which is nice because then you don't have to worry about them tipping over and breaking. You've got weighing boats. Everyone know what a weigh boat is?
No.
So when you measure the mass of something, you don't want to pour it directly on the scale, right? That's a bad idea, because then you got to clean up the scale. So basically, it's just a little piece of plastic with a lip around the edge of it that then you pour your reagent into, and then you weigh that. So you subtract the weight of the boat, and you measure the mass of the chemical inside. And the nice thing about them is that they're made of plastic, so you just tip them over, everything comes sliding nicely out into a beaker or a flask, whatever you want to put into. And you have a nice clean balance that hasn't completely coated with nasty chemicals. So there should be a ruler, a thermometer, 1 glass test tube. Why do you think we have 1 glass test tube and the rest are plastic? What do you think we can do to glass that we can't do to plastic?
Heat it up.
Exactly. Yeah, you can't put a plastic test tube in a flame. That's a really bad idea. So yeah, I imagine that's the one we'll be heating under the flame. So there's some plastic spoons, pair of tweezers. a candle, cardboard box, and there should be a balance in there. I need to check my box because I don't think I did get my balance. So obviously, a lot of you who are bakers will have a balance in your kitchen. That's a really good thing to have if you like, for baking in particular, where you need to be very, very precise about, you know, flour and things like that. Instead, a lot of recipes now, instead of having like cups and everything for flour, they will have grams. And so you can measure them very, very precisely. How many people have a balance in their kitchen? Not many?
I have a gram scale for my cooking.
There you go. Yeah, well, that's what it is. Scale, balance, it means the same thing. Yeah, because originally, I mean, everyone's probably seen like a triple beam balance, where like, you know, you move things around. Like if you've gone to your doctor's office and they take your weight, they actually put you on a balanced scale, and so they move little weights around. Well, that was the original way of measuring mass, and so we still call them a balance today, even though it's really a scale. So these are the different labs we'll be doing and the different things that you'll find in there. So this is the what I was mentioning for burning. Basically, it's an ethanol gel that you just set on fire. Like I said, it's the sort of thing you put under a chafing dish. You should have a well plate. It's basically a plate that has like either 12 or 16 or 96 little individual wells in them where you can put liquids. Balloons, that's going to be fun. Syringe and some vinegar. We're going to be doing a Kool-Aid experiment. That'll be fun. We're actually going to be separating the different colors in Kool-Aid by a process called chromatography, which is something we'll be talking a little bit about. Anyone know? Can anyone tell me what they think chromatography might mean? What does chroma mean?
Color.
Color, exactly. So chromatography basically came from the separation of colors. And that's what we're going to be doing. And then we're going to be physically separating the different colors used to make that particular brand of Kool-Aid. So yeah, so just I've posted this on the Canvas page, like I mentioned, under lab resources. So go through there, make sure you have everything in there. Some of these things you'll be able to just get at a grocery store, like Ziploc bags, like a wooden stirring rod. That'd just be like basically a coffee stirrer. But there's some other things you probably won't be able to get, like the rubber stoppers, and you know, something to push it through. Yeah, Kool-Aid, you can definitely get that at the store. But some of these things you won't be able to find, like, you know, 0.1 molar solution of magnesium sulfate isn't something you can just run down to the store and get. But if there are some things you can just get, you can just go ahead and get them. Some of the ones that are a little bit more specific, like the iron sulfate, magnesium sulfate, copper wire, for instance, you may not be able to find those. So have a look at the list and check and make sure you have everything. Okay. So any questions about the list? I was just going to go ahead and move on to the next topic. Anybody have any questions about what they should have and where they can get it if they don't have everything?
What do we do if we're missing something important?
Oh yeah, just send a message to myself and Musa. Did you get the I can type his address in the chat, so you can. Okay. Yes, because he will have backups of all this stuff. So yeah, particularly the solutions. He's probably got gallons of that stuff in the lab, so he can get you like a little container if that's one of the things you're missing.
Are you gonna have the list up on Canvas?
Yes, it's under lab resources. I think it's like the fourth or fifth thing. And it just basically says Chem 210 home lab checklist. And then it has that exact file. So you can just run all the way through it, make sure you have everything. Okay. So I guess in class, it sounds like Dr. Schubert is talking about separation and purification techniques. Is that true?
She hasn't really gone into specifics yet.
Okay. So we'll talk a little bit about that today and have a little, oops. So if you're going to be doing like organic chemistry or biochemistry, those two in particular, separation and purification to be something you're going to be doing all the time, because you're going to get like complex mixtures of things, and then you're going to want to separate, like for instance, you're going to want to separate hydrophilic molecules from hydrophobic molecules, ones that like being dissolved in water and ones that like being dissolved in oil. You're going to, like if you're a synthetic organic chemist, for instance, you're going to take 2 or 3 or 4 or more reagents and then mix them together and then make something new. Well, you're going to want to take that something new you've got and remove it from all the other stuff so you can actually study it. So you need to separate them and you need to purify them. So we're going to learn about a couple of different separation techniques. We're going to go into groups again, and we'll find out that there's basically 2 ways to separate things. There's chemical means and there's physical means. Now, a chemical mean would be taking advantage of the fact that some chemicals react differently than others. Like for instance, hydrophilic, something like alcohol, which easily dissolves in water, like methanol and ethanol, are so-called short chain alcohols. They dissolve easily in water. But if you have like a really long hydrocarbon backbone, like with carbon and hydrogen, a really long chain of them, and a little alcohol group in the end, those don't like being dissolved in water at all. And so you can easily separate those things just by mixing like water and some sort of organic solvent like ether or benzene or something like that. Shake them together, and they'll separate like oil and water. They'll just separate, and all the things that are more hydrophobic will stay in the organic layer. All the things that are hydrophilic will stay in the water layer. That would be like a chemical separation. Now, physical separation, what do you think is involved with that? If I wanted to separate something physically, what does that mean?
It's like taking it apart.
Well, if I was to take something apart, that would mean I'd be breaking it down, probably chemically, and I don't want to do that. So how would when I talk about separating something chemically, what would be something about that molecule that would be different from another molecule that I could separate them, that isn't chemical? Well, different temperatures? No, because basically molecules don't have a temperature. A solution has a temperature, but not individual molecules have a temperature. Color, interesting. How would you separate them based on color physically without using chemistry? That's tricky.
Sorting?
Density, excellent. Or sorting, that's exactly what I'm getting at. Density or sorting. If you're sorting something, like if you've got a sieve, let's say like, gold miners or gold panners, back in the 1850s, all came out to California to get gold. How did they separate their gold, little gold nuggets they would find, from other like rocks and mud and stuff like that? How would they do that? They didn't use chemistry to separate them. What did they do?
Panning?
Panning, exactly. And how does that work?
Well, they had multiple techniques using them. The most simple one is just by grabbing something with holes and just moving it around.
And so how would you separate the gold from the rest?
You would have to separate it from its source.
And what is it about gold that makes it that you could separate it from all the other things?
Extraction.
You're doing, well, yeah, you're doing a physical extraction, but what I'm sort of getting at, what is it about gold that makes it possible to separate it from, mud and rocks and
denser.
Other things? It's denser, exactly. It's much more dense. So what they would do is that they would get their gold and whatever other rocks they've found, and when they do the panning, what that would do was actually the heaviest stuff, the densest stuff, would sink to the bottom. And so the gold would sink to the bottom, and then the lighter bits of the dirt and whatever else that was in the mud would stay close to the top. And then they dump out the top, and then they put in some more, and then shake it around so that more dense gold would sink to the bottom. They just keep doing it and doing it and doing it till eventually they'd find maybe like 2 or 3 small little really dense pieces of gold at the bottom of the pan. So that would be a physical separation based on density. So we'll break into groups, and we're going to look at a number of different techniques. And what I want you to do is to look up something about the techniques. Do just a little bit of research. Get some of the main ideas about how this. Tell us a little bit about get a picture for one thing. What would this separation look like? Is there a machine that does it? How would you do it? How does the machine work? And what principles does the separation take place? So get a picture. What kind of things can be separated? Can we separate anything based on this particular thing, or do we need to actually is there a specific set of molecules that you need? Like, for instance, panning. Could you do that with anything? Could you do that with a gas? Could you do it with 2 different liquids? Like, what sort of things? What I'm going to do, I'm going to put this link, and that'll bring you to this particular page, and then you can edit it. So I'll just put that in the chat. There you go. So these are the different techniques. So we've got evaporation. So group 1 will be like evaporation. So the people in group 1, put your names there, and then give us a picture of on the slide of what are we talking about? What are the different things you could separate one from another using evaporation? The next technique is extraction. Now, a chemical extraction has a very specific meaning. So when you look it up, extraction could mean pulling a tooth. So we want you to look for chemical extraction. That is a very specific chemical meaning. So that would be using a chemical to extract another chemical from a complex mixture. Next group, sieving and filtering, sort of like what we've just been talking about. What does that mean? How would you use a molecular sieve? What is a molecular sieve? What sort of molecules could you separate using that technique? Crystallization is one. If you're going to be synthesizing certain things. One of the ways you can isolate it from everything is by turning it into a crystal. So like if you have something that certain things will crystallize if you put them in the cold, like they're not very soluble at cold temperatures. So you can take something, put it in the fridge, and you'll notice, like particularly with a lot of larger molecules, they will tend to crystallize and form a solid and then sink to the bottom. What sort of things can you actually do? What sort of things can be crystallized? What are the conditions used for crystallization? Centrifugation. Can anyone tell me what centrifugation means?
Like spinning?
Yeah, spinning. That's basically all it is. But with the centrifugation or centrifugation, depending on what part of the side of the pond you're from, you spin these things really fast. Like sometimes you can separate things based on spinning them as slowly as like 1,000 RPM. But there are also scientific centrifuges that spin up to 100,000 RPM and faster, where you can separate things based on really, really small differences. The smaller the difference, the faster you need to spin them in order to separate them. And that'll be the last one. So you have 5 different groups. So as sort of like we did before, have someone in charge of getting everyone else involved. Like, don't everyone unmute so you can talk to each other. I'm going to give you about 10 minutes to get into your groups and look up the different things, and then we'll come back and talk about each individual one. Is everyone clear about what we're going to be doing? Has everyone checked the link? Is that working?
Yes.
It is? Excellent. I'm always terrified of these Google shared work. It's like sometimes, you get like more people than it's ready for, and the whole thing explodes or whatever. So hopefully it's working. So what I will do is put people into groups. All right, so. All right, so there we go. I'll come around and check out, see if anyone doesn't have a group, let me know. Okay, pretty much got everybody back. Let's see what we have. Okay, so who in group 1 is the presenter?
Me.
All right, take it away.
So my group did evaporation, and all liquids can evaporate at a room temperature, and normal air pressure may evaporate. Element or compound transitions from its liquid state into its gaseous state, because when water evaporates, it changes from liquid to a gaseous state, like I said before. And from our research, we discovered that homogeneous mixtures can be separated using evaporation, as evaporation separates the liquid components from the physical components inside the mixture. And
okay, what's a homogeneous mixture?
A homogeneous mixture, I keep thinking that I remember it, but I can't remember specifically. It's like a homogeneous mixture is when there are 2 substances, but
it could be a lot more than 2.
Yeah, it could be more than 2, yes. And I keep forgetting the definition. Sorry. can't remember
Yeah,
this.
there's one basic difference between like a heterogeneous mixture and a homogeneous or homogeneous mixture. You know what the basic difference is?
With a heterogeneous mixture, you can tell the difference. Like, if there are like multiple liquids, you can tell them apart. Like,
Yeah, more or less. But really what it means is like with a homogeneous mixture, if I take a sample of a homogeneous mixture, any part of a homogeneous mixture, it'll be exactly the same. So, but if I have a heterogeneous mixture, if I take a sample from the top and I take a sample from the bottom, they're going to be different.
Oh, they'll be different.
So for instance, like if I have like a saturated salt solution where there's a little bit of salt on the bottom, well, if I take a sample from the top of the solution and one from the bottom, they're going to be different. There's going to be more salt near the bottom than at the top. So that would be a heterogeneous mixture. Like milk, when we say it's homogenized, it goes from being a heterogeneous mixture where you have fat on the top and milk on the bottom. And when it's homogenized, then it's the same all the way through. So that's basically what that means.
Thank you.
Yeah, no problem.
An example of evaporation is that table salt is acquired from the evaporation of seawater, and the heat is then emitted from the sun. Basically, just wait for the seawater to evaporate, and then we can harvest the table salt from what remains. And from this, from our research, we didn't really see that evaporation is a chemical change, so we assume from this example that it was a physical change.
That's right. That's right. Yeah. The changing of, so that's something else we're going to learn later in the term. The changing from a gas to a solid to a liquid is a physical change, not a chemical change. And that's something that high school students like really have a hard time with. Like when you boil water, it's still water. A lot of them seem to think that you've changed it to hydrogen and oxygen when you boil water, which would be a really bad idea because then a lot more kitchens would blow up every time you made pasta. So you know that that's not the case. So does anybody have any questions for Lance? You just did too good a job, man. Right.
Thank you.
Great job. Okay. Who's giving the presentation for group 2? Oh.
Amanda and I.
Okay. All right, take it away. Go ahead.
So one thing that I would like to ask you before I begin, when we say extraction,
yep.
When we want to isolate a chemical from a solution, or that will be purification?
Well, these are all purification methods. Purification just means separation. Purification just means you're separating something from another thing. Extraction is basically when you're taking advantage of the fact that something is more soluble in one liquid or in one solid than another one. You're basically you're separating in the terms of solubility. That's basically what chemical extraction means.
Okay, so
yeah.
Here we put as an example, soap and water.
Mm-hmm.
For example, if we want to put them apart, we will add salt into it, and it's depending the amount of salt that we add, we want to make soap from one side and water from the other.
So what happens when you add the salt? What happens to what is it? What happens to the soap when you add the salt?
I'm not sure.
But you basically it separates from the water, right?
Yeah, by density, right?
Well, I don't know if most of you know that like most detergents have two different pieces to them, a hydrophobic side and a hydrophilic side. That's why they're so good at cleaning things. Because you can clean both, and they usually have a charge on them, usually either positively or negatively charged. So when you add the salt, it basically gets rid of the charge, and then the soap is no longer charged, and so it is no longer soluble in water, and it will separate into something else. That's when you say you're salting out something. That's usually what that means. So what are some of the other types you found? I see you've got coffee and tea examples. Can you explain how that works?
Yeah. So the three most common types of extractions are liquid-liquid, liquid-solid, and acid-base, which is also known as chemically active extraction.
Mm-hmm.
And the coffee and tea examples are both of the liquid-solid type, where a compound, in this case caffeine, is isolated from a solid mixture by using a liquid extraction solvent, and it would be the water. So extractions are a way to separate a desired substance when it's mixed with others. The mixture is brought into contact with the solvent in which the substance of interest is soluble, and the other substances that are present are not soluble in this solvent. The extraction is using two immiscible phases, so these are phases that don't mix, such as oil and water, to separate the substance from there's something on your screen that's popped up and it's blocking. So it separates the substance from one phase into the other, and the physical property would be solubility.
Okay, cool. So you're not just extracting caffeine. So coffee wouldn't taste very good if that was the only thing you extracted was caffeine. And with tea, you extract all kinds of things. So let me ask you a question. Would you get a different extraction if you used cold water versus hot water?
I think doing it with cold water would take longer.
Right, because certain things, because the hotter things are, generally the more soluble they are. So actually that's how you make decaffeinated coffee, is that you take coffee and you extract it with something like an organic solvent. And that extracts like the really hydrophobic compounds like caffeine. And then you extract those, and then when you do the water extraction in your coffee maker later, that is gone. So, just excuse me for a sec. My dogs really want to go for their walkies, and so they're getting rambunctious, so I had to deal with them. Yeah, excellent job. Yeah, I completely forgot about coffee and tea. That's such an excellent example. Anybody have any questions for the group? Yeah, good job. So who's group 3? Who's presenting for group 3?
I'm presenting.
Can see who is that?
Oh, Jexy.
Oh, Jexy. Okay, excellent. Okay, here you go.
Okay, so sieving and filtering is actually extremely simple. It's just a form of physical separation. I don't think many of us use filtering that often, but it's used. Basically, what it does is it separates the larger particles of a solid from a liquid, because the liquid is easier. Can pass through because it's a smaller particle, but since the solid is too big, it can't pass through. And for sieving, it is essentially the same thing, except it's for just matter also. So it's separating larger particles from smaller ones. So for sieving, it'd be something like gravel and flour, or gravel and sand, but for filtering, it'd be something like mud and water. So, yeah.
So how do you actually, could you make different filters to filter different things?
Yeah, I'm pretty sure you could. Sorry, I don't know that much actually.
So what's actually in the filter that allows the liquid to go through, but the solids are kept behind? So the filter actually has to have something in it that allows the liquid to flow through. What would it have in it?
Usually something like a complex set of layers that keeps out the solids but lets the liquids go in.
So it's got to have pores, right? Yeah, I mean, that's basically the only difference between filtering and sieving. Filtering, the pores are microscopic in size; they're really, really, really small. And then when you have a sieve, they're much, much bigger. Then with a colander, they're really big. So it's just all a matter of what size things you're separating, and that's why when you go into the lab, there is like hundreds of different kinds of filter paper. You can't just use any old filter paper, depending on what it is you're filtering. But yeah, excellent. I love the presentation. The pictures are awesome. So anybody have any questions for him? Everyone's so quiet. All right, thanks, Jexy. All right, who's presenting for group 4?
I'm presenting for group 4. Gage.
Gage? Okay.
Yep.
All right, go ahead.
So, oh, it doesn't have the Breaking Bad in there. Dang.
Yes, certainly some crystals involved with that, isn't it? Yeah.
So crystallization is being able to purify a solid. So what it's able to do is a solution is heated, and basically crystallization is used through solubility. So because a hotter solution is able to compounds are more soluble in hot liquids, so it's able to create a...
Generally, yes. With solids generally are more soluble in hot water. Not all of them, but the vast majority.
And after the solution is heated, it's given time to cool down, and this is when a crystal-like solid appears. And then the impurities are able to be filtered out, and then you're left with just crystals. And when they're cooled. There are many different types of ways to crystallize. It's not only through heat. You can use many different types of techniques. We didn't have much time to go into the other types, but there's like 8 other types. But the 3 most common ones were evaporative crystallization, cooling crystallization, and reactive crystallization. Let me see if I can pull this up real quick. Basically, evaporative is if instead of trying to make the solid soluble, you actually evaporate the solution. And what's the other one? Reactive. I cannot find that one. But yeah.
Yeah, I mean, basically what you're doing is you're taking something that's soluble in a solvent, and that's something actually in your notes there. The purpose of crystallization is to purify an impure solid. So which is the solvent and which is the solid?
So the solid is like a I don't know, I could be like salt, I guess.
Right. Yeah, the solid's what you're trying to crystallize. The solvent is the liquid. So yeah. So basically, what you're doing in all of these things is you're taking something that's soluble in the solvent, and you're turning into something that's insoluble. And there's lots of different ways to do it. And yeah, you've given us some. And yeah, and you get these pretty crystals. And yeah, this is one of the most used techniques ever. And what people do is called just recrystallization. They purify something by crystallization, and then they dissolve it again, and then they recrystallize. And every time you recrystallize, you lose more and more of the impurities. You tend to lose a lot of your chemicals that you're looking for too, but it gets purer each time you do it. So yeah, great job. I like the crystal pictures are always nice to look at.
Thank you.
All right, last group, centrifugation. Who's giving the presentation?
I can present.
All right. Oh, you mean you didn't agree? All right. Francesca, taking charge. I love it. Okay, what have you got?
Oh yeah, so ours is centrifugation. Basically, it's a technique to separate particles like in a physical manner from solution, depending on their size, shape, and density, viscosity, and can be dependent on how fast or slow the centrifuge spins.
Mm-hmm.
So types of mixtures that can be separated are heterogeneous mixtures that you can see the different types of how they look physically. Some examples are like milk, how you explain homogeneous milk, how that is separated, powders and liquids. Another example is blood.
Mm-hmm.
They can use those, as you can see in the picture that we have on the right. You can see like the different layers within what's inside the blood. Another example is like your washing machine. Once it's on spin, it kind of takes out the water from your clothes.
Yep.
Is another example. And then the advantages to using this type of separation method is seeing the different densities of your different mixtures. And yeah, it separates the different particles according to their size and shape and density.
Yeah, mostly on the density. Yeah, if some things are different sizes, they tend to be different densities. If things are different shapes, they tend to be different densities as well. Like if you have something that's like a really forms like a very small particle that's very dense, it will be spun through whatever medium to the bottom of the tube. So the things near the bottom of the tube are more dense than things at the top. So yeah, excellent job. Did you ever figure out what the difference between serum and plasma?
No.
Okay, yeah. Serum basically is we allow the blood to clot. So if you just leave blood like sitting at room temperature, it will eventually clot, and so all the red blood cells will just fall to the bottom. If you spin it before you allow that to happen, then you've got plasma. So generally, plasma is cleaner than serum. Serum has all kinds of stuff in it from the clotting process that plasma doesn't. So some tests in the hospital require plasma, others require serum. It depends on someone must have like given blood recently or something. If you go in, you notice that they use different types of tubes when they're collecting your blood. If they're doing a blood test, some of them have different colored tops on them. No one's noticed this?
Yes.
Okay. That's because some of them have chemicals in them like heparin, which prevent clotting from taking place. And so you'll collect plasma from those, and then other ones will allow clotting to take place, and then you'll get serum from those. That's the difference. Thought you might want to know. Anyway, all right. Thanks so much, everybody. Anyone ever any questions about any of these differences? There's something we're going to be doing, especially dealing with liquids and gases and solids. We're going to be dealing with that a lot later on. There's some really interesting chemistry there involving like thermochemistry and heat and energy and all that kind of good stuff. But yeah, right now we're dealing with the differences between homogeneous and heterogeneous mixtures, and these are all different techniques you can use to separate those. So anyone have any questions about what's going to be due this week as far as the lab goes? Everyone just pick up the kits and send in some kind of proof that you've got everything. If you don't have everything, I put Moose's contact information in the chat, so you can email him directly. And that'll be it till Thursday. And there go the dogs again. So I'll see everybody on Thursday. There's no more questions. Okay?
All right. Thank you, Professor.
All right.
you.
All right.
Thank you.
All right. We'll talk to you soon.
Thank you.
All right. Bye-bye.